So example one says sketch a graph of y equal to -5 and evaluate the integral from 1 to 4 of -5 dp. So let me make a quick little sketch of the graph. The function y is equal to -5 is just a horizontal line. And so I'm going to draw a horizontal line here, and then I'm asked to evaluate it from 1 to 4. And so you will remember when we are evaluating the integral, we are finding the area under the curve. And when I say the area under the curve, I mean the area between the x-axis and the function. So this integral makes a rectangle. It has a width of 3 and a height of -5. It's negative because it is below the x-axis. And so the area of a rectangle is length times width. And so the value of this integral would be 3 times -5, which is -15. Number two, it says sketch a graph of y is equal to -5p and evaluate the integral from 1 to 4 of -5p dp. So this is a linear function. It has a negative slope and a y-intercept of 0. So it is going through the origin with the slope of -5. And I'm just going to estimate the slope here. It doesn't really matter. It doesn't really need to be exact for our purposes here. And so again, I'm going to find the value of the integral from 1 to 4. And so I am finding the area of the shaded region here. So this is a trapezoid. And to find the area of the trapezoid, it is height divided by 2 times base 1 plus base 2. The height in this instance is given by the x values. So the width of the bounds, it goes from 1 to 4. So my height is 3. And to get the bases, I'm going to take the bounds and plug them into the function. So if I take 1 and plug it in, I have -5 times 1, which is -5. And then if I plug in 4, I have -5 times 4, which is -20. And so that's going to give me 3/2 times -25. Therefore, my area is going to be -75 over 2. And that is the value of the integral from 1 to 4. So on the next one, it is similar to the one that we just did. It says sketch a graph of y is equal to -2x plus 4 and evaluate the integral from 1/2 to 3/2 of -2x plus 4 dx. So let's sketch the graph. I have a y-intercept of 4. So it's going to cross the y-axis at 4. I have a slope of -2. And so since I have a slope of -2, it's going to go down 2 and over 1. Down 2 and over 1. So the graph of my function looks something like this. And since I am integrating from 1/2 to 3/2, I'm going to find the area under the curve of this shaded region right here. And just like the last example, this is a trapezoid. So I need the height given by the x values. It goes from 1/2 to 1.5. So my height is 1. And then to get the bases, I'm going to take the bounds and plug them into the function. So I plug in 1/2. -2 times 1/2 is -1. And -1 plus 4 gives me 3. And then I plug in 3/2. 3/2 times -2 gives me -3 plus 4. That gives me +1. And so I have 4 times 1/2. So the value of this integral is the area of the trapezoid, which in this case is 2. Any questions on the first 3 examples there? Okay, well, let's look at the next one. You should be able to recognize this as a semicircle. And the reason it's a semicircle, I'm going to write the formula for a circle. X squared plus y squared is equal to the radius squared. And if I solve for y here, I have y squared equals r squared minus x squared. And then I'm going to take the square root of both sides. So I have y equals plus or minus the square root of r squared minus x squared. And so this is the positive half of the semicircle. If you have the plus or minus, it would be the whole circle. My radius is 4. So graphing the semicircle with a radius of 4, y equals the square root of 16 minus x squared looks something like the figure that I just drew. And notice that I am evaluating from -4 to 0. Therefore, the area under the curve that I am finding is this right here. Okay, so the area of a circle is pi r squared. If it were the whole semicircle, it would be pi r squared divided by 2, but I have 1/4 of a circle in this case. So my formula is going to be pi r squared divided by 4. And I know that my radius is 4, so I'm going to take 4 and plug it in, which means I have 16 pi divided by 4, which gives me a value of the integral equal to 4 pi in this instance. So is there a question on that one? Well, let's take a look at some of the guided practice here where we evaluate the integrals and drawing a graph if necessary. So I have the integral from 1 to 7 of 3 dx. So this is just like the first example that I did. I have a constant, so this is going to make a rectangle. The width of my rectangle, it goes from 1 to 7. So my width is 6. My height is 3. Therefore, the value of this integral will be 18. The next example, I have a linear function. When I have a linear function, normally it will make a trapezoid. So to find the height of the trapezoid, I look at the bounds, the x values. It goes from 1 to 7. So my height is going to be 6. And this one is just like the second and third examples that I did above when it makes a trapezoid. So to get the bases, I'm going to take the bounds and plug them into the function. So I plug in 1 and I get 3. And then I plug in 7 and I get 21. And so that gives me 3 times 24. And so the value of this integral is 3 times 24, which is 72. And in example number 3 here, I'm going to use my rules. So remember that we have 7 rules for definite integrals. And one of those rules allows me to write this as the integral from 1 to 7 of 3x dx plus the integral from 1 to 7 of 4 dx, splitting these two terms up into 2 separate integrals. And so when I do this, I can evaluate this, which I just did in example number 2. The value of the integral from 1 to 7 of 3x dx is 72. We just found it. And then the integral from 1 to 7 of 4 dx, that's going to make a rectangle with a width of 6 and a height of 4. Therefore, the value of that part will be 24. And adding those two things together gives me a total of 96. So in number 4, this is also going to make a rectangle, but the first thing that you should notice is that the bounds are out of order. So I am going to use one of my rules, the reversing limits rule, and write this as the integral from 0 to 5 of 2 dt. And when I do that, I have to put the negative outside the integral. So now, since I have a rectangle, the width of the rectangle is 5, the height is 2. Therefore, the area under the curve is 10, but I need to make it negative since I reverse the limits. So this is going to be negative 10, and it's negative because we are going backwards. And we had to reverse the bounds of the integral. Same thing for this one. The bounds are out of order, so I'm going to make this the negative integral from 0 to 5 of 2t dt. Normally, when I have a linear function, the ones that I did previously, it made a trapezoid, but in this case, sketching a quick graph, it goes through the origin, and I am integrating from 0 to 5. So in this case, I don't have a trapezoid. Since it goes through the origin, I have a triangle. And to find the area of the triangle, it is 1/2 the base times the height. My base is 5. To get the height, I'm going to take 5 and plug it into my function. And 2 times 5 gives me 10. Therefore, 1/2 the base times the height will give me an area of 25. But since I reverse the bounds, I need to make this negative. So the value of this integral is negative 25.
How did the one above it give you a trapezoid then? How did 2?
So if my bounds had been different, like if I had integrated this from 1 to 5 or from 2 to 5, then I would have to have a trapezoid. But since the bound starts at the origin, it makes a triangle. So it was helpful to sketch a graph in this instance.
Okay.
Does that make sense?
Yeah, it makes sense.
Okay, so the last one here, I have the integral from 5 to 0 of the absolute value of 2t. And so my bounds are out of order. So I'm going to reverse this, making it negative. The integral from 0 to 5 of the absolute value of 2t dt. And then I have the negative out front. And then on this one, I'm also going to sketch a quick graph. the absolute value function makes a v at the origin. And I am going from 0 to 5. So this is just like the last one. I'm going to have a triangle with a base of 5, a height of 10. And so the value of this area will also be 25. But since I reverse the bounds, I have to make this negative. So this one is equivalent to negative 25 as well. Okay, so let me stop right here for just a second. Any questions over anything on the first page that we have done so far? Okay, well, I need you to turn to the second page. And let's look at the charts here. We got a little review of our trig derivatives. You should know these.
That's adorable.
So let me fill these in, and I'm going to pause for just a second so that you can think about the answer. The derivative of sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. The derivative of tangent is secant squared of x. Derivative of cotangent is negative cosecant squared x. And the derivative of secant of x is going to be secant x tangent of x. And the derivative of cosecant is negative cosecant x cotangent x. So a quick little review. We're going to use some of those in what we're about to do. But let's look at, we'll call this the Jeopardy version, where I have the derivative f prime of x, and I need to work backwards to get the original function. So my derivative is 7x. So I need to work backwards to get my original function, and I'm going to let you try it for just a second. So think about the derivative of what would give me 7x. Well, you should have come up with 7/2 x squared. And if you got that, you were almost right, but not completely right. Okay, so if I take the derivative of this, I take 2 and multiply it times 7/2. So 2 times 7/2 gives me 7. And then I subtract 1, which gives me x. And so you would think that that would be right. However, look at this, for example. What is the derivative of 7/2 x squared plus 8? It's 7x. And what's the derivative of 7/2 x squared plus 450? Well, it's also 7x because the derivative of a constant is 0. So there are literally an infinite number of functions that could all vary just by the constant, that when I start with the derivative and work backwards, there's literally an infinite number of answers because they could all vary by the constant. And so in order to account for that, I have to put a big plus C here, denoting that this could vary by any constant. So using that information, let's look at the next one. I have 4x minus 7. And so the derivative of what function would give me 4x? Well, that would be 2x squared. Derivative of 2x squared, 2 times 2 gives me 4. I subtract 1, that gives me the x. And the derivative of what would give me negative 7? Well, it would have to be negative 7x. And then I need to put in the plus c. Well, looking at the chart of the table that I filled in above, the derivative of what gives me cosine of x? Well, that would have to be sine of x plus c. And then the derivative of sine of x, the derivative of what function gives me sine of x? That would have to be negative cosine of x plus any constant. And so what we are doing here when we are working backwards here, we are not taking the derivative, we are taking the, let's wait for it.
Mr. Newhouse,
Yes.
how is it negative? Oh, never mind. I'm stupid.
Okay, because
Proceed.
okay, the derivative of cosine is negative sine. So in order for this to be positive, this has to be negative.
Yeah, I got it.
Okay, so what I'm doing here, I'm not taking the derivative, I am taking the antiderivative. And the antiderivative, this term is equivalent to the integral. They are used interchangeably. And so what I want you to recognize here, okay, is that when we are taking the antiderivative, we're working backwards to get the original function from the first derivative, and that is equivalent to what we were doing on the first page. We are finding the area under the curve. So if I start out with f prime of x equal to 3x squared plus 6, I can write that as the integral of 3x squared plus 6 dx. And this is how I solve for it. Okay, let me go back to this example. When I take the derivative, and let me say at the beginning, we will do this a little bit more extensively later on, right? But when I take the derivative, I multiply the exponent by the coefficient and then I subtract. So multiply and subtract. So when I do the antiderivative, I got to do the opposite. So instead of subtracting, I'm going to add, and instead of multiplying, I'm going to divide. So for example, I have 4x, and that's raised to the first power. So I'm going to add 1 to my exponent. So that gives me 2. That's x squared. And then I divide. 4 divided by 2 gives me 2. Same thing on this one. I start off with an x to the first power. I add 1 to it, which gives me the x squared. And then I divide the exponent into the coefficient. 7 divided by 2. And I end up with 7/2 x squared. So.
Oh, okay. We didn't see your example.
You did not? Oh.
No.
Okay. I didn't really write anything. I was just explaining how I got from 4x to 2x squared and 7x to 7/2 x squared. Okay, so let me see if I can do that right here. Okay, I want the integral of 3x squared plus 6. So I'm going to add 1 to my exponent. I have an exponent of 2, so I add 1 to it. That gives me x to the third. And then I'm going to take that and divide it into the coefficient. 3 divided by 3 gives me 1. And then I'm going to do the second term. The antiderivative of 6 is going to be 6x. And then I need a plus c. And so now let me check it. What's the derivative of x to the third plus 6x? Well, it gives me this back, 3x squared plus 6. Okay, so the connection that I want you to make here is that when I start with the derivative and then I work backwards to the original function, that is the same thing as integrating here, and it's finding the area under the curve like I did on the examples on the first page. And so on the next one, I have the integral. I'm going to take this and write it as x to the 1/2 dx. And I should also say that in these expressions, when we are writing them in integral notation, you must have an integral, which is the beginning. The elongated s there denotes the beginning of the expression. And then you must have a dx, which denotes the end. It doesn't have to be a dx. It's whatever I am integrating with respect to. So if you will look back at the examples on the first page, it could be a dp or a dt or a dx, whatever the variable is there. In this case, it has to be a dx because I'm integrating an x variable. So working this one, taking the antiderivative, I have an exponent of 1/2. I'm going to add 1 to it, which gives me x to the 3/2. Then I'm going to divide. So I have the new exponent and I divide that into 1, which means I'm just going to flip this and multiply. So I also need a plus c there. And let me check it. If I take 2/3 x to the 3/2 and I take the derivative, I should get this back. So 2/3 times 3/2 gives me 1. Then I subtract 1. 3/2 minus 1 gives me 1/2. And I end up with x to the 1/2 or the square root of x back.
Question house.
Yes.
Can you go over how you multiply by 2/3?
Yes. Okay. So I have x to the 3/2, and then I need to divide by the new exponent. So I have 1 divided by 3/2. And when I divide by a fraction, that is the same as multiplying by the reciprocal. So I have 1 times 2/3, which gives me just 2/3. Does that make sense? So in other words, anytime your coefficient is 1, you're just going to take the exponent and flip it and multiply by the reciprocal. I'm going to do one more example and then we are going to stop for the day, but this example is a little tricky. So let me see if you can figure it out. I'm going to write this as the integral from -3 over x plus x to the 4th. And then I need to close it with a dx. So see if you can figure out the value of this integral.
Yeah, I got the second part, but -3/x is pretty puzzling.
Okay, well, let's take a look at it. So here's maybe this will help you. The first thing I'm going to do is split these up. So I can write this as the integral from -3/x dx plus the integral of x to the 4th dx. So I need a plus c. And then let me work this second one. I'm going to add 1 to my exponent, which gives me x to the 5th. And then I divide. So 1 divided by 5 gives me 1/5, x to the 5th. And so that takes care of the second term, but then I have -3/x dx. Well, I could write this as the integral of -3x to the -1. The problem with this is when I add 1 to my exponent, I get 0, and then I'm dividing by 0, and I can't do that. So I am going to use one of my rules here. And so the rule that I'm going to use is the constant multiple rule. So I'm going to move the -3 out and write this as -3 times the integral of 1/x dx. I can do that because -3 is a constant, and according to my constant multiple rule, I can move any constant outside the integral and then multiply it. Then I need you to dig down deep in your calculus brain there. Let's say I have a function like the natural log of x, for example. What's the derivative of the natural log of x? Well, f prime would be 1/x. Yes? So if my derivative is 1/x, then working backwards here, the value of this is going to be -3, and then the integral of 1/x dx is going to be the natural log of x. So this would be -3 ln of x plus 1/5 x to the 5th plus c.